Over time, we have developed various travel methods that connect us between points in the shortest time possible. From the bicycle to space rockets, our continuous quest for enhanced efficiency and speed has only peaked. While the concept of faster-than-light travel is popular in science fiction, real-world scientists have been working hard to get us to that level. And finally, a novel discovery. Is it possible to travel faster than light? In this video, we would be discussing the latest speed, as scientists discovers a new way to travel faster than light. In light of new discoveries of space exploration, the Alcubierre drive and Lenz's warp drive proposal has ignited imaginations as a potential key to travel faster than light. The Alcubierre drive is a speculative warp drive idea proposed by theoretical physicist Miguel Alcubierre in 1994. He describes the Alcubierre drive as a theoretical means of traveling faster than light that does not violate the physical principle that nothing can locally travel faster than light. Think of the warp drive like a magical bubble around your spaceship. Now imagine a spaceship preparing for a journey to a distant star. With a traditional engine, the trip would take decades, or even centuries. With a warp drive, it squeezes space in front of the spaceship and stretches it behind. It's almost like folding a piece of paper, but instead, you're folding space itself. The crew experiences a moment of distortion, and when the warp bubble collapses, they find themselves near the target star, having traveled across the vast distance in a fraction of the time. While Alcubierre's theory fits well with Einstein's equations for how space and time work, unfortunately, this concept, while tantalizing with its dream of zipping through space at extraordinary speeds, comes at a considerable cost. Massive energy demands and the reliance on exotic matter, a substance that remains purely theoretical and unverified in real-life scenarios. The need for such exotic matter raises practical challenges and skepticism among scientists, akin to requiring a magical ingredient for a recipe, one that may not even exist. This leaves many questioning whether the Alcubierre warp drive is a captivating idea on paper or a concept with practical viability in the vastness of space. Subsequent variations, including a 2010 update by former NASA engineer Dr. Harold G. Sonny White, reduced the energy requirement but retained the need for exotic matter, although in diminished quantities. Building more on its predecessor is the Lenz's warp drive proposal, proposed by Dr. Eric Lenz, a physicist with over 10 years of practical experience. Dr. Eric Lenz's groundbreaking warp drive proposal heralds a new era in space exploration, offering a fresh perspective on the elusive dream of faster-than-light travel. Rooted in conventional physics, Lenz's innovative approach stands out for its potential to reshape the future of interstellar journeys, sidestepping the need for exotic matter that has long posed a theoretical hurdle. The key distinction in Lenz's vision lies in the strategic placement of energy around the warp bubble, the theoretical construct essential for warping space and facilitating faster travel. This departure from conventional methods hints at a more efficient utilization of energy, addressing a critical challenge that has plagued earlier warp drive concepts. The reduction of the energy requirement stands as a central goal in Lenz's proposal, representing a leap toward a more viable and realistic warp solution. By reconfiguring how energy interacts with the warp bubble, Lenz aims to make faster-than-light travel not just a theoretical concept, but a tangible and attainable prospect. In the ongoing saga of the warp drive concept, Dr. Lenz's variation. Lenz's idea is still just a theory, and some people doubt if it could actually work in real life. Theoretical physics, where these ideas come from, doesn't always mean they'll turn into something we can use practically. Critics say we should be skeptical until we have proof from experiments showing that the warp drive is doable. Even though Lenz wants to use less energy than previous warp drive ideas, there's still a big challenge. We're not sure how to generate and handle the energy needed to go as fast as he's suggesting. His plan is built on certain assumptions and theories, and some people question if these ideas are really solid, especially when dealing with complicated stuff like bending space and time. Even if the theory is good, actually building a warp drive for a spaceship is a tough job. We might need technology that we don't have yet. There's also worry about what happens when we start messing with space and time. Critics are concerned about unintended consequences and how it might affect everything around us during space travel. Lentz is trying to avoid using exotic matter, but there are still questions about whether the materials or energy sources needed are possible or safe. Finally, the lack of real-world tests or evidence supporting Lentz's warp drive makes some people think it's more of an idea on paper than something ready for practical use right now. Another group of researchers from Switzerland, known as Applied Physics, proposed their own concept. Interestingly, their drive eliminated the need for exotic material to create a warp bubble. However, their model couldn't surpass the speed of light, the ultimate goal of space travel. Advancements in the warp drive field are accelerating, propelled by Lentz's vision and the collective determination to transform theoretical concepts into tangible realities. Researchers are exploring novel ideas, conducting experiments, and refining theoretical frameworks, all with the aim of bringing warp drive technology closer to practical application. Dr. Lentz expressed the possibility of patenting his warp drive, emphasizing that his work is part of a rapidly growing body of research in this area. The surge in new warp drive concepts since Alcubierre's 1994 proposal provides hope that a testable version may be closer than anticipated. Lentz highlighted the excitement surrounding the recent progress in warp drive research. As we trace the trajectory of Lentz's warp drive advancements, the once distant prospect of faster-than-light travel takes shape on the horizon. Lentz's vision serves as a dynamic force, propelling us toward a future where stars are not merely distant points of light, but potential destinations within our reach. The measurement of the speed of light dates back to 1676, when Rømer observed the moons of Jupiter. Precision came in 1879 with the Michelson-Morley experiment, establishing the speed of light at approximately 186,282 miles per second, a foundation for various measurements. Light travels at different speeds in various mediums. In substances like air, water, or glass, it slows down due to interactions with tiny particles, resulting in phenomena such as refraction when light transitions from one medium to another. In the vacuum of space, where there is no matter, light accelerates significantly, moving at about 299,792 kilometers per second. Distances in space are measured in units like astronomical units, light years, and parsecs. An astronomical unit represents the average distance from Earth to the Sun, approximately 93 million miles. This unit is useful for relatively short distances, such as gauging the space between the Sun and its planets or stars in a binary system. Now, consider the mind-blowing concept of a light year representing the distance light travels in 1 year, roughly 5.88 trillion miles. Picture this. It's almost 800 times the diameter of our entire solar system. For perspective, the closest star is around 4.2 light-years away, and communication with our nearest spiral galaxy would take a staggering 2.5 million light-years. When astronomers study distant objects, they are essentially peering into history. Objects that are 10 billion light-years away appear to astronomers as they looked 10 billion years ago, providing a glimpse into the universe's early stages after the Big Bang, which occurred about 13.8 billion years ago. The parsec, approximately 3.26 light-years, derived from parallax second, is a useful tool for astronomers, employing parallax to measure stellar distances, akin to the way an object appears to shift against the background when viewed with one eye and then the other, a cosmic ruler for measuring space. The faster you go, the heavier you become, a phenomenon comparable to the increased weight felt when driving a faster car. Achieving the speed of light through conventional means is deemed impossible, leading to intriguing concepts like wormholes and warp speed. Transitioning to the subject of time dilation, a phenomenon occurring during high-speed travel, astronauts on the space station experience a slight shift into the future. They age a bit more slowly. Consider the example of traveling to Alpha Centauri, approximately 4.5 light-years away. If magically zipping there at 99.9% of light speed for 4 Earth years, your experience is a quick 2 weeks, while back on Earth, 4 years have elapsed. The time-space effect creates a fascinating scenario where either time on your spaceship crawls super slowly, 110 times slower, or you cover a distance 110 times shorter. A unique cosmic perspective. Sending a message back to Earth presents another challenge. Even a robust signal takes a whopping 4 Earth years to return. Exploring space at high speeds poses significant challenges, primarily the colossal energy required to accelerate. In the realm of physics, a rule dictates that the energy needed to increase speed grows exponentially. Doubling speed requires 4 times the energy, and tripling speed demands 9 times more energy. A formidable energy puzzle. Traditional space travel methods, such as rockets, encounter difficulties when aiming for higher speeds. This challenge has spurred scientists to explore unconventional ideas, including the M-drive, a propulsion system that doesn't expel anything. However, skepticism abounds, as it appears to defy known principles of motion. Recent tests by physicists at the Dresden University of Technology disputed promising results from NASA and China, attributing them to false positives influenced by external forces. The clear challenge is evident. How do we achieve exceptionally high speeds without an astronomical energy requirement? While some concepts, like the M-drive, raise eyebrows, scientists are actively seeking innovative ways to accelerate space travel, an adventurous scientific journey to crack the code and explore the stars. As scientists conceptualize and test new ideas, the potential for solving this challenge comes into view. Envision a future where we traverse space at unprecedented speeds, all rooted in overcoming this formidable energy hurdle. The Alcubierre drive and Lenz's warp drive, theoretical concepts rooted in speculative physics, offer tantalizing possibilities for space exploration. As our current propulsion methods fall short for interstellar travel, these warp drive theories present a potential solution. By distorting space-time around a spacecraft, they could theoretically allow for faster-than-light travel, enabling us to reach distant planets and explore far-off galaxies. However, practical application faces formidable challenges, chiefly the need for vast amounts of energy. Efforts to overcome this hurdle include the exploration of space-based energy sources. Solar probes, venturing close to the Sun, aim to unlock the secrets of harnessing solar energy efficiently. If successful, these missions could provide the energy required for implementing warp drive technologies. Imagine a future where humanity taps into the boundless energy of space derived from our own star. This energy could then power the exotic propulsion systems, potentially revolutionizing our ability to explore the cosmos. Beyond facilitating planetary exploration, the Alcubierre drive and Lenz's warp drive could propel us towards the study of distant galaxies, unlocking new realms of scientific understanding. In essence, as we strive to harness energy from space through solar missions, the successful culmination of these endeavors could pave the way for turning speculative theories into practical tools for interstellar travel and unraveling the mysteries of the universe. Do you think we will ever be able to travel faster than light? Leave your comments below. Also, like this channel and subscribe to be up to date with the latest contents. Thank you.